So let's get started. Hello, everyone. Welcome to the webinar Water Determination in Cannabis. My name is Luisa Schubert and I'm responsible for the event organization. So if you have any questions, please use the Q&A button. They will be answered at the end of the webinar or during the webinar. And we will be launching a survey and asking you to participate. So your feedback will help us to continuously improve our webinars. And of course, we will send you the materials in a follow-up email. So thank you for joining. And now I would like to hand you over to the speakers.
So also from our side, hello to everybody and welcome to the today webinar about water determination in cannabis. My name is Christian Funke. I'm application specialist for titration here at Xylem Analytics, SE Analytics. I'm with Xylem Analytics since 2015. And yeah, from my education, I'm an environmental engineer.
Yes. Good afternoon, good morning. Yeah, my name is Stefan Kaus. I'm the product manager at Titration. I'm with Cannabis with Analytics since 1919. I'm trained as a chemical laboratory technician, and after that I completed an engineering degree and in chemistry. So I will change now the camera that you can see me. Hopefully it works. Yes, it works. Okay, now. So before we start with a webinar with the water donation in cannabis, I will explain you a little bit about the history of titration here at Analytics, where we are coming from, and what we're doing here at Analytics. So it started in 1937 with the development of one of the first pH electrode. We have a shot has a patent on that. It was 1937, and first usable pH electrode. So and also in the 40s, shot started with the production manufacturing of glass viscometers, and okay, these two parts, the manufacturing of glass electrodes, other electrodes, and glass viscometers and special glass tubes, calibrated glass tubes were put together in one daughter company called Schott Instruments. In Germany it was Schott Geräte, but in English it is Schott Instruments. It was 1973 in a smaller town between Frankfurt and Mainz, Hofheim. And also in the 70s, we started then with manufacturing of pH meters, viscosity measurement systems, and since 1978, we also manufacturing titration instruments. So until 2000, we were in Hofheim, smaller town again, between Frankfurt and Mainz. So we moved 2001 back to the headquarters of Schott in Mainz. But it happens that Schott decided to go out of the laboratory business. So they sold us to Novalytics, which is a US-based company. And they also bought other companies like WDW, WTW, Epro, Bellington Stanley, and other companies, and created a company called Novalytics. So it was very successful until 2010, and Nova decided to sell this business to a big international corporation company called ITT. This was 2010, and 2011, this big international company with 40,000 employees were split into 3 independent companies, and one of them were Xylem. So this started the name Xylem. And since 2016, we are now part of Analytics is part of Xylem Germany. And other brands are WW, Epro, and Sensortechnik Weinsberg here in Germany. So that's the history, the timeline. And yeah, we are based in our site is in Mainz, which is in more or less in the southwest of Germany. It's close to the Frankfurt Rhein-Main airport, so it's very easy to access. We have approximately on this side about 140 employees. We have And but we have in Germany, we have for Xylem Analytics, we have approximately 600 employees. Where in Weilheim is the headquarter. We have and then we have in Ingolstadt a site, and in East Germany in Sachsen we have Sensotechnik Mainzberg. So 140 employees working. Here you can see the building at the SCHOTT site, working mainly in the production, but also in research and development, order processing, sales, and marketing. Yes. And coming to the products we are manufacturing here, we have mainly the production of electrodes, pH electrodes, redox electrodes, temperature sensor for lab and field, and also for process. And this is one of the major products we have. The next product is the automatic titrators and piston barrettes. And another instruments we are manufacturing here is the capillary viscometry, the capillary viscometers itself, and the automatic measurement systems for viscometry. So as I told you before, we are part of Xylem. So Xylem has worldwide 17,000 employees, but Xylem Analytics has about 1,500 employees. And this is what you see here is the brands for the laboratory business, laboratory analytics business. We have here the Bellingham Stanley, which it's a brand for refractometers and polarimeters and density meters. Then we have EPRO brand. We have measuring temperature devices and data lockers, and for validation, and it's also used in the laboratory, but also in the cold chain. Companies like Aldi and Lidl using using this data lockers. Then we coming to the US companies, our brand, our analytical, which are manufacturing TOC and chemical flow analyzers, and also sample preparation instruments for gas chromatography. And the next brand from the United States is YSI, making biochemical analyzers and other systems. So, and last but not least, we have the WTW brand or WTW brand for spectrophotometers, photometers, pH, conductivity, dissolved oxygen turbidity meters for lab and fields. And yeah, that's all the product change we have here for laboratory business. So you can see on the next slide, again, a little bit the products. We have here the pH and conductivity sensors and so on from WTW and Analytics brand. We have multimeters and turbidity meters from WTW, and we have here the temperature sensors and data lockers from EPRO, titrators from Analytics, and viscometry from Analytics. And so here on the picture you can see a refractometer from Bellingham Stanley. So I guess I'm through the introduction, the short introduction, and I will hand over to Luisa again.
Yes, thank you, Stefan, for the good instruction. But before we get into the deep details, we have one question for you. So I will start a survey. So please take part in this. And the question is, do you already perform Karl Fischer titration? It's a question we would like to know from you. Okay. At the moment, it's okay. You have 20 seconds left to answer the question. So at the moment, round about 50–60% didn't perform Karl Fischer titration. Okay, I will close it. So 41% did already perform Karl Fischer titration, 51% didn't, and 7% have it in mind. Just good to know for you, Christian and Stefan. Then you can start. We don't hear you, Christian. We cannot hear you.
I guess now you can. Sorry.
Yes, perfect. No problem.
Sorry. Okay. Okay, so let's start with the webinar. And first, I want to give you just a short overview about the content of the today webinar. We will start with why are we interested in the water content of cannabis, and how is the water content determined according to pharmacopoeiaThe. Is the second point. Then we will talk about the Karl Fischer titration, just a little bit theory, and the separation between direct and indirect titration. I will describe how we make the determination of cannabis, how we detect the right oven temperature, which is one of the main points, and what reproducibility we reach with our procedure. And of course, the last point is a short summary of our results. Okay, so let's start. Why are we interested in the water content of cannabis? Hemp or cannabis in general is, let's say, quite an interesting plant. It is a raw material for a lot of industrial application, just like fibers for textile industry or in construction, or also in the paper industry. The hemp seeds can serve as a healthy food, but also for animal feed. In the European Green Deal, which has the aim to be the first climate neutral continent until 2050, hemp also plays its role. Hemp is a very good carbon pool. Just to give you some numbers, about one hectare of hemp can bind up to 9 to 15 tons of CO2. And it has, in combination with this, it has a very good growth rate of about 5 months. Due to legalization processes, I guess all around the world, also in Germany, the medical access of hemp is also of increasing interest. For example, in pain therapy, but also for cancer therapy. The treatment of cannabis hemp changes, especially in the USA, but also in other continents, countries, with the Agriculture Improvement Act of 2018. In this act, this was the first time that the differentiation between cannabis and hemp was done. And this differentiation was based on the THC, so the tetrahydrocannabinol content, which is the main active alkaloid in cannabis. And on this concentration, the differentiation was based. In this act, a level of 0.3% was chosen to separate this. And this is important because a concentration above 0.3% THC would lead that the cannabis falls under the Controlled Substance Act. Below it, it is treated as hemp, and then it's no longer a controlled substance. And the important point here is that the concentration, not only of THC, but also of other compounds like CBD, it is always related on the dry weights. So we need to normalize it, and the dry weight is here the main factor. And therefore, it is important to get the exact water concentration of the cannabis. In addition to this, the water content is also important for the storage of the cannabis. A water content of 10 to 12% might lead to a microbial growth, and therefore also here it's important to know the water content. In Europe, in the European Pharmacopoeia, on the 1st of April this year, a new supplement was introduced. And this was the first monograph which treated or explains how cannabis is treated in Europe. In Germany, there was for a longer time a monograph available, which also was the base for this European monograph. And this monograph defines that the water content is determined as so-called LOD, the loss of dry. And how is this done? Is you take 1 gram of the cannabis, it's pulverized or cutted, and dry it at 40 degrees under medium vacuum over molecular C for 24 hours. So what you see here is that these are very mild conditions over a very long time. So normally the LOD is determined, for example, at 100 or 105 degrees. So here we take 40 degrees and we increase the time. Medium vacuum is defined as 1.5 to 2.5 kilopascal. So also a very wide range, so not very specific. The problem with this LOD is that you will not detect just the water, but also the volatile compounds like essential oils or terpene, which they will also evaporate in this procedure. So that means we will always get a higher content, which not only relates to water. The Karl Fischer titration offers here an alternative, which is very selective and selective for water and a very reliable and good known titration. Karl Fischer titration, so what is the principle of the Karl Fischer reaction? The basis of this reaction is the so-called Bunsen reaction, which is defined for aqueous system. So we have water, iodine, and SO2, which reacts to sulfuric acid and HI. And the German chemist Karl Fischer then tried to transfer this into a non-aqueous system just to be able to titrate the water content. And he took an alcohol, mainly methanol or ethanol, added SO2 and a base, in former times pyridine. Nowadays, it's mainly imidazole or an imidazole derivate. And these 3 compounds react to a sulfite ester. And in the presence of water and iodine and an excess of the base, the sulfite ester reacts to a sulfate ester. And as soon as the water is completely titrated, you get an excess of iodine. And this excess can then be detected by the titration system. We can differentiate in the Karl Fischer titration between 2 different, let's say, systems or principle. And the difference between these 2 systems is how we add the iodine. So we have volumetric systems, which is, let's say, kind of a classic titration. You have a burette, you have an iodine solution in different concentrations, which is then dosed to your solvent with a sample, and the reaction takes place here. And this kind of titration is suitable for both for liquid and solid samples. And then we have the coulometric water determination. In this case, the iodine is not dosed to the titration cell, but it is produced electrically by use of a generator electrode, and the amount of iodine can then be calculated afterwards by Coulomb's law very precisely. And this kind of titration is then only suitable mainly for liquid samples and solid samples only indirectly. The volumetric water determination, yeah, just to define it generally, is mainly taken for higher water contents, and coulometric for lower concentration, but this strongly depends on the sample and how good the sample dissolves and how much of the sample you can dissolve. So you see that the difference between both systems is only the kind of the addition of iodine. The detection is in both cases the same. Okay, we then used the system, the direct titration, to detect the water content of the cannabis. So that means direct determination. We just took a methanol-based solvent and added the sample directly to the titration cell. So quite simple equipment, but you can see in the titration curve that this is not really suitable. You have the main compounds or the main water at the beginning, but then the titration curve is continuously increasing. So that means the water is extracted very, very slowly and not fast enough, and you will not find the entire water you have in your sample. And therefore, of course, also reproducibility is quite poor. So we change now to the lab. So I will change the camera. Okay, we have just to show you the systems prepared here, our instrument a little bit. You can see here on the very left side such a volumetric system. So you can see here on the top the barrette, the exchangeable head with the iodine solution. This exchangeable head has an RFID chip on which all the information is stored. I told you at least in one sentence that different concentration of the titration reagents are available. So the real concentration is stored on this RFID chip, and even if you have different solutions here, you can easily remove the exchangeable head and add a new head. Then we have here the closed titration cell. So it is very important to have a closed cell because the ambient water always has an influence on the result. As I told you, this is a very selective method. We have here the magnetic stirrer, and in this magnetic stirrer, a pump is included, so it's quite easy to remove or add fresh solvent. On the titrator itself, you can find a lot of some main default methods for one component and two component system, and also for the titer determination. For different kind of standards, you find ready to use methods. Okay, but we saw on the graph this direct method is not really suitable. Therefore, we changed to such a system you can see now on the screen. So this is still a direct method, but now the main problem was that the extraction time is not fast enough with the first system we used. So therefore we wanted to increase the extraction time by heat. So we added a heatable magnetic stirrer here, and we titrated it in the boiling heat. You can find here also, so we added a cooler just to cool the solvent down, and that it comes back to the titration cell. And we added a homogenizer to extract really all of the water, to make the sample smaller and yeah, just to increase the extraction of the water. So the result here can be seen then now on the next slide. So you see we have added the water, we added the sample again directly. We used an extraction time of about 300 seconds, and you can see now in the curves that the water was titrated quite fast and with a good endpoint here. But here the problem is that it's not that easy to use. When you are titrating the sample in the boiling heat, you need, before you add the sample.
I think for some people it's not clear how they can show the camera on the larger screen. On the Zoom, you can find it the few options on the right above side. It's called View, or in other languages, and then you can use side by side option, and then you can adjust the screen of the presentation and also from the camera. I'm not sure if this is clear. No? Okay. So you can make the screen from the camera larger, and you can see more.
Okay. Vielleicht kann Jens uns ansonsten noch was reinschreiben in den Chat.
Maybe.
I will write something in the chat. I will do it.
Okay, thanks. Okay, where did I stop? So the problem is here, as I explained, we are in the boiling heat. We have to remove this cap here before we can add the sample. And you can imagine, if you're in the boiling heat, you open it and the solvent can release via the opening here. So you have to let it cool down at the beginning. And it's not easy to get all of the sample into the titration cell. So therefore we get the results you can see on the slide now. So the mean value is at 8.8%, but the RSD is quite poor with above 4.5%. So it's possible, but let's say not ideal. And so with this, we are coming to so-called indirect titration methods. What is an indirect titration? In case of an indirect titration, the water is extracted outside of the titration cell. And then when the water is extracted, you can transfer the solvent or whatever is used into the titration cell. So examples for this is an external extraction in a vial with solvent, or what we are using in our experiment here, the determination via an oven. The colorimetric Karl Fischer titration with headspace oven, you can see the scheme on the picture here on that slide. So you have a dry carrier gas like nitrogen or air. You have a vial with a sample which is inserted in the oven and heated to the used temperature. Then the dry carrier gas goes into the vial via a needle. Is taking, so via an inside needle, the carrier gas takes the water and transports it via the outer needle to the titration cell. And this kind of system can be used for samples which cannot dissolve in KF solvents, or maybe lead to side reaction, or only release the water at high temperatures. Yeah. Okay, so going back to the laboratory, you can see now here such an oven system. In this case, we have the titrator here, which is, let's say, a normal Karl Fischer colorimetric titrator, and the system already runs, so we can see it working. We have an oven and we have a sample changer. And the system is not only available in this configuration, but you can use it with sample changer or without the sample changer. And if you use it without the sample changer, the oven system can also be controlled just by the titrator, not only by a computer software. And you can see in this case, the entire system works completely automatically. On the sample changer, we can add up to 49 positions plus 1 zero vial. We have here again a magnetic stirrer. Looks quite same like the one for the volumetric system, but here in this case we have also a pump, but not only a pump, also a valve. And we have here the option to use either dried air from the ambient, so the pump sucks in the ambient air, dries it via this molecular sieve here at the back. You can see it here at the back, and then we have here a flow meter. You can control here the gas stream, and then it goes into the vial with the sample, and then into the titration cell. Yeah, at the beginning I told you we can use dried air, but we can also use an inert gas like nitrogen, and then the valve switches between the input of the air and the input of the nitrogen, and then of course the pump is not used. The KF titrator, you can see now here the difference. On the volumetric system, you found there the exchangeable head. Here in this case, we do not have an exchangeable head, but we have this generator electrode, and the iodine is produced electrochemically directly in this solvent. And also on this system, of course, default methods are available so that you can use the system directly. Yeah, the system directly. Okay. So what was our or how did we prepare the sample? At the beginning, we have such cannabis flowers. Hope you can see it. So let's say quite big and not really, we cannot really introduce it into the vial. So therefore we grinded it a bigger amount to have a homogeneous sample. And after that we weigh in the sample, in the vial and close it. And the nice thing is now that after you have weighed it in the vial, you have kind of fixed it, because you do not have any exchange or whatever with the ambient. So the water you have here is now in the vial and nothing can happen here more. To grind the sample, we used a normal coffee grinder. And there you have to be a little bit careful, because the sample can heat up during the grinding process, and then you can lose water. For our experiment, it was not that important, because we were just interested in the let's say relative water amounts, but in the routine it might be good to have a cryogenic grinder which cools automatically the sample and avoids in that way the loss of water. Okay, and then the first interesting point here was how can we or what is the right temperature? So at what temperature do we have to make the measurements? And to detect the right temperature, we used or measured a so-called temperature ramp, which you can see here now on the slide. The weight was about 80 milligrams. You can see two curves because we used two hemp samples. So these were THC-free samples, so CBD cannabis. We measured between 40 to 200 degrees with a heating rate of 1 degree per minute. And we took every 10 seconds a new measurement value. So what can we see here in the curve? We see that at the beginning, the main part of the water was released. Then the drift goes down, has the lowest part, let's say, between 100, 110 to 150 degrees, and then the drift increases again. So in this part, we can say for sure that we have there any decomposition processes. So let's have a closer look to the interesting parts from 100, 110 to 160 degrees. And now you can see that we have two minimums here. One at about 110 degrees and the other one at about 150 degrees. So in between, the drift increases again, and then we get the second minimum, and then it increases continuously. So the question here was what happens between 110 and 150? Is there water released, which was stronger binded by the cannabis, or is this already a decomposition process? So that was the interesting question here. So therefore, we took some, or we make a so-called linearity test. So first, you can see here one example for the titration curve from the oven. It looks like a classical Karl Fischer curve. The drift or the water content is at the beginning released very, very fast, and then you have a smaller release at the end, and then all water is titrated. Okay, we made then, as I said, a so-called linearity test at 110 and 150 degrees. We used for both temperatures 6 different weights between 20, 25 microgram to slightly above 80 microgram, and calculated here the mean value and the standard, respectively, relative standard deviation. So what we expect at 110 degrees, we got a mean value of 9.16% with a very good RSD of 0.4. And at 150, we detect more water, nearly 10%, with a higher RSD of 1.5%. Then we made a graphical analysis. We plotted here the water content against the weight. And what we can see here are 2 things, 2 points. First point is the correlation between the correlation factor between the measurements. And you can see in both cases that we get a correlation factor of 1, and in the other case at 150 degrees of very, very close to 1. So this is perfect in both cases. But the next thing is the ordinate intercept. This should be theoretically at a weight of 0, also 0. Just from experience, we can say that an ordinate intercept of 50 micrograms is acceptable. And here we can see that the ordinate intercept, or in case of 110 degrees, is at about 30, but in case of 150 degree, it is at 180, minus 180. So it seems that something happens. The higher the weight is, the more water we get relative, and therefore the slope changes, and the ordinate intercept is then too high. Yeah, that I already told you. 110 degrees, we got a good correlation and an ordinate intercept close to 0, independent of the sample weight. Okay, so that leads for us to the conclusion that 110 degree is the right temperature, and we used this temperature to make or to detect the reproducibility, and we made now a repeat measurement with the weight of about 50, slightly below 50 milligrams, and we get the results nearly similar to the linearity test. So the mean value was 9.15% with an RSD of close to 0.6, which is for a natural sample quite good. Okay, so just to give a summary, what are the advantages of the Karl Fischer open method? We get very selective results, and in this case, it's an indirect method, and we can be sure that only the water is determined in this titration. The result is observed in under 30 minutes, so related to the pharmacopoeiaThe procedure with the loss of dry very, very fast. We have smaller sample quantities compared to the pharmacopoeiaThe method, and the results are very reproducible. And the sample handling is quite simple. You just have to grind it, weight into the vial, and then everything is fixed here, and no exchange with the ambient, and can then be easily measured. Okay, so if you are even more interested in this topic of water determination in cannabis, you are welcome to download our cannabis white paper. If you are interested in more general information about Karl Fischer titration, you can discover our landing page to get more information about this method. And with that, thank you for your attention, and we are open to your questions.
Thank you, Christian. So I'm a little bit surprised because we have 0 questions. So really,
so everything is clear. So the explanation was really good.
Yeah.
And everything is clear. That's good.
Yeah, so thank you for attending our webinar. At the end of the webinar, so when you leave it, a survey will pop up. So please take part in the survey, because we will continually improve our webinars for you. And of course, you will get your certificate of attendance and your materials in a follow-up mail. So have a nice day. Thank you for joining, and we will see us hopefully next time. Bye-bye.
Okay. So also from my side, thank you. And see you.
Bye-bye.
Bye.